In the previous video, we looked at the basic design of crystalline silicon solar cells, and we started our discussion of the losses that occur in solar cells. We have introduced spectral mismatch losses. We will now continue with the additional losses that occur in solar cells, such as reflection and transmission losses, parasitic absorption, and shading losses. We will use the standard crystalline silicon solar cells shown here to demonstrate each of these additional loss mechanisms. Part of the solar cell module surface is covered by a metal grid. As this metal grid is not transparent to the incident light, the area under the grid is shaded. Shading by the front metal grid therefore decreases the amount of sunlight reaching the absorber layer. The metal grid is not the only factor that prevents light from entering the solar cell. The glass plate used to encapsulate the solar modules reflects a fraction of the incident light as well. Even though silicon dioxide is highly transparent to visible light, it's not completely so. Some light is therefore reflected off the front surface of the solar cell. The third additional optical loss concerns the notion that light is absorbed in all the layers of the solar cell. However, only the photovoltaic absorber layers contribute to the actual generation of charge carriers. This means that any light absorbed in the photovoltaic inactive layers is considered a loss mechanism. This loss mechanism is known as parasitic absorption. Parasitic absorption is of special concern to solar cells with a PIN junction, where only the intrinsic I layer is photoactive layer. PIN cells will be discussed later in this program. Finally, we consider the transmission losses. Transmission losses are caused by photons passing through the solar cell without being absorbed, due to the limited optical thickness of the solar cell. This generally involves photons with energy equal to or slightly above that of the band gap. These photons have a lower absorption probability and are therefore less likely to be absorbed in the solar cell. In the electrical losses section, we consider the recombination losses and other losses. Recombination losses occur when an electron, and after excitation, falls back to its initial energy state. If this happens, the absorbed energy is essentially lost and cannot be converted into electrical energy. Earlier in this course, we introduced 3 different recombination types. The first type is radiative recombination. In radiative recombination, the energy of the electron is emitted as a photon after recombination. The energy of this photon is the same energy as the band gap of the semiconductor material. Radiative recombination is very significant in direct band gap semiconductors, but relatively rare in indirect band gap semiconductors like crystalline silicon. The next process to which excited charge carriers can recombine is Auger recombination. Auger recombination is a 3-particle process. The momentum and energy of the recombining hole and electron are transferred to another electron or hole. This third particle is excited deeper into respective band and relaxes again by a process called thermalization. Finally, there is the Shockley-Reed-Hall recombination. Shockley-Reed-Hall recombination is an indirect recombination mechanism that is facilitated by an impurity atom or a lattice defect. The defects introduce energy levels within the band gap which facilitate carrier recombination. Shockley-Reed-Hall recombination is therefore of particular interest at the surface of the solar cell or at the interfaces of different layers in a solar cell. At the surface of a semiconductor, the crystalline silicon lattice terminates. Therefore, many valence electrons cannot find a partner for creating a covalent bond. This results in so-called dangling bonds, which in essence are localized defects that may trap a charge carrier. In fact, for semiconductors that hardly have any defects in the bulk of the material, the recombination might be dominated by the surface recombination. To what extent each of these recombination types occurs depends strongly on the properties of the used material. Finally, there are the other electrical losses. These involve the resistive losses and shunt losses. To understand the resistive series losses and shunt losses, we first look at the equivalent circuit of a solar cell. Here you can see the so-called single diode model for a solar cell. There's a lot going on here, so let's move through our schematic step by step. The first thing you may notice is the current source on the left side of the diagram. This represents the photocurrent generated through illumination, which we call here the I photon. Ideally, we want to pass the photocurrent to our load, represented in purple on the right. We also see the diode with a current ID passing through it. This represents the solar cell diode characteristics in the dark. Some current will pass through this diode, and this current does not reach the load. This actually represents the recombination that occurs in the solar cell. Next, we see two resistors, Rp, the shunt resistance, and Rs, the series resistance. These two resistors are there because the solar cell is not an ideal diode. The series resistance is caused by bulk resistances of the semiconductor materials and the metal electrodes. The contact resistance between the semiconductor and the metal also influence the series resistance. As you can gather from the equivalent circuit diagram, increasing the series resistance decreases the maximum output power. The series resistance should therefore be as low as possible. Next, we look at the shunt resistance. If you remember, this resistance is parallel to our load, so we actually want it to be as large as possible, otherwise it acts as a sink for current that will reduce the power to the load. A reduced shunt resistance is caused by leakages across the PN junction around the edges of the solar cell, or defects, pinholes, and impurity precipitates in the semiconductor material. So this is what the full overview of losses in any type of solar cell looks like. We can translate these loss mechanisms into three major solar cell design rules. The losses due to the spectral mismatch are subject of the spectral utilization. The additional optical losses are the main concern of the design rule known as light management. The electrical losses are considered in the band gap utilization design rules. Designing any type of solar cell involves a delicate interplay between these three pillars. In summary, in this two-part video, we discussed the basic function of each of the layers in a standard crystalline silicon solar cell. We looked at an overview of all the optical and electrical loss mechanisms that occur in any type of solar cell. Finally, we derived from these the universal solar cell design rules. With this last video, we conclude the first course in the solar energy program on the fundamentals of photovoltaic energy conversion and the role in the energy transition. In the next course entitled Solar Energy, Photovoltaic Materials, Devices and Modules, we will discuss the wide variety of existing PV technologies. The knowledge of this course on fundamentals will act as a basis to understand the design concept of the various PV technologies. We will discuss the fabrication processes of PV technologies used by industry. Finally, we will discuss the advantages, limitations, and future challenges of all these PV technologies. I hope to see you back in the next course.